Welcome to VFD Vibes, your place for all things related to variable frequency drives. If you're interested in how to make things turn, or manufacturing technology in general, then this is the place for you. I'm your host, Greg Weichman, and today we're diving into a foundational, but often misunderstood, aspect of VFD applications, power system configurations. Now, what we most commonly see is a neutral grounded, Y-connected, three-phase system. But that's not the only way that three-phase systems can be configured. Today we're going to dive into what the others are and what implications they might have to your VFD installation or application. To help make sense of it all, I'm joined by Joe Pottebaum, an application engineer who's worked with just about every power configuration out there. Together we'll break down what each system type means, where they show up in the real world, and what you need to watch for before ever hitting that start button. Joe, thanks for being here today.
Thanks, Greg.
Could you give our listeners a little insight into your background?
Sure. I graduated with a Bachelor of Electrical Engineering from Ohio State University, the Ohio State University, and I've been working in the field of AC drives since around 1980. So I was right there at the inception of the AC drive revolution, and started out in the design and development of AC drives, then moved into applications, applying these to solve customers' problems. I've been doing that with Yaskawa since, the year 2000.
Fantastic. I'm also a Big Tenor going to UW-Madison, although we're not always on the friendliest terms with Ohio State. Let's start simple on this topic, though. What do we mean when we say power system configuration?
Well, I think the first distinction we have to make is between single-phase power and three-phase power. And when we say power system configuration, we mean just how are the wires put together in order to create a power system that would power motors, lights, and all that type of thing. So the first distinction I guess we want to make is between single-phase and three-phase power. And what is the difference? Well, single-phase current can only produce an alternating magnetic field that's back and forth no matter how we arrange the coils. Three-phase current can produce a rotating magnetic field, and a rotating magnetic field is really convenient when you want to run a motor. What else? Well, single-phase power requires 2 wires, three-phase power requires 3 wires. Single-phase power works well for heating elements, light bulbs, personal computers, and televisions, and three-phase power works best for motors. Yes, there are single-phase motors, but they all require some mechanism to create a rotating field to get started. Once started, the rotor inertia can keep the motor spinning in the presence of the alternating field created by the single-phase current. It's sort of like a one-cylinder lawnmower engine.
I could see that, because with one cylinder, your piston could get stuck top dead center or bottom without that inertia to get it past the peak.
Well, that's why lawnmowers come with a rope to start them. So if you don't want to start your single-phase motor with a rope, you need some sort of centrifugal switch or something in order to create that rotating field. And some single-phase motors do have an extra winding built in and a little centrifugal switch to turn it on and off when the motor finally gets started. Others use things like shaded poles, and there's many ways that create single-phase motors. Electric clothes dryers, for instance, run on single-phase, and they have a little switch that you have to hold in. We all experience that, where you have to hold the button in until the drum starts spinning, and that's in order to get the motor started. By the way, the largest single-phase motor in the catalogs is about 10 horsepower. Beyond 10 horsepower, the starting requirements become more or less impractical.
So you mentioned three-phase is better for rotating loads, and single-phase is better for smaller loads. Even rotating loads we have in our home seem to be single-phase. Is that what we have in our home typically?
Exactly. Single-phase power is the most economical for small loads. You only got to run 2 wires into the house, actually 3, but we'll get into that. Hence, it's most commonly used in residential and light commercial installations. And I'd say mostly used because single-phase often shows up in very remote locations because the power company only wants to run 2 wires out there to power the transformers. So you get out in the middle of western Nebraska or something, you may encounter the only power available is single phase.
So that might show up quite a bit in farmland irrigation and things.
Yes.
And in that case, you need to take that single phase. And my guess is because you have pumps that are much bigger than 10 horsepower, you're probably converting it to three phase.
Well, that's right. And in fact, one of the things we've done in the application department is figured out exactly what a single phase rating for a typical drive would be. If the drive's designed for three phase, the typical single phase rating is somewhere between a third and a half of the three phase rating of the drive. And you have to look in the catalog to find out what that single phase rating would be. And there's a lot of caveats that you have to adhere to when you're trying to run a three-phase drive on a single-phase source. Now, Yaskawa does have a product which is called the single-phase boost converter, which is designed to actually convert that single-phase AC into a regulated DC bus that can now power the drive through its DC terminals. We sell that product, and that product is used primarily in remote irrigation systems.
And that's a solid-state product, too.
Yes,
correct?
that's a solid-state product. It's not a rotary converter, so it's truly solid-state.
But this all sounds like way too much work if I have a factory that needs lots and lots of motors. So I'm guessing that's why factories are going to be fed directly with three-phase power.
Right. Almost all industrial facilities in the United States use a three-phase distribution system. Single phase just isn't practical for anything beyond. In fact, if you look at your house, the largest load that you have in your home is going to be your air conditioning system, and that's typically 2 to 3 horsepower. Most of the other loads, like clothes dryers and light bulbs and heating elements, they're fine with single phase. When we talk about single phase systems and we talk about the single phase configuration, the most common single phase configuration is the 240 volt line to line with a center tap neutral. This is the configuration you find in almost all houses. You've got 240 coming in, and that's split into two 120 volt circuits. And this configuration with that center tap can provide the 120 volts line to neutral that comes to all the wall sockets. A little plug that you want to plug a lamp in, the wall plugs, these are all 120 volt single phase. Of course, clothes dryers and air conditioners and electric stoves, these run on the 240 volt directly because they're bigger loads. Everything else is 120 volts. Now note that I described that center wire as neutral and not ground. That's important, even though neutral is always connected to the ground at the service entrance. The neutral conductor, which is the white wire in a house, is at ground potential but is allowed to carry current. The ground wire, the green wire, is not allowed to carry current. So even though both the ground and the neutral are at ground potential, you can have current go through the white wire and return to the transformer, but the green wire is not allowed to carry current. Now, this is not allowed to intentionally carry any current. Of course, there's always leakage and there's always capacitive coupling and all that. And so there will always be some current in that green wire, but nothing intentional.
And when you say intended to, under normal operating circumstances, it is actually intended to carry current
when there is a fault, yes. If you have a fault where you get a short to ground, then there'll be current in that green wire, and the green wire has to be big enough to carry that current till the breaker can clear.
So in your home setup, you've got the two hot legs that come in and they get split in your, used to be a fuse box, now it's a circuit breaker.
Right.
With the neutral in the middle, and that's why when you slide your circuit breakers in, they go between one hot leg and neutral, and that's how we get our 120. And then when you need 240 for a device such as an electric stove or dryer, that breaker will actually connect to both hot legs.
That is correct. Absolutely.
And then at that box, is that where neutral is tied to ground?
Exactly. Back in your fuse box or breaker box, that's where the service, the electrical service, comes into your home. That's the service entrance. And at the service entrance, the neutral and ground are connected together.
Okay.
Now, even though both neutral and ground wires are ground potential and are in fact tied together at the service entrance of the building, only the neutral can carry current. Consequently, loads can only be connected from line to neutral. You cannot connect a load from line to ground.
That helps me understand power at a home level, at a smaller load level. but really we're here to talk about VFDs and motors in a factory setting. So how does this all change when we transition over to three-phase?
As mentioned before, three-phase current can create a rotating magnetic field. And the three-phase power evolved out of electric motor development. Okay, in 1887, that's quite a while ago, Nikola Tesla filed for a patent application on a three-phase electric motor design. In 1888, a fellow named Mikhail Dobrovolsky developed a three-phase electrical generator and a three-phase electrical motor. In 1891, the same gentleman exhibited a three-phase, three-wire transmission system at the International Electrotechnical Exhibition in Germany. And the key point is that it only takes three wires to power a three-phase motor. No neutral connection is required. So this goes back to the 1890s when three-phase was developed because it gave you a compatible generation system that could actually run motors. And in most industries, almost all of the load in any given industry is motors.
You started this whole podcast by explaining that the key fundamental is that it creates a rotating magnetic field. And what I don't think a lot of people realize is anything that moves, even when it's moving straight, is powered by a rotating source. And what did you just say? What percentage of loads are?
Well, I do a little presentation for grade school kids on motors and magnets. And what I tell them is if it's not alive and it's moving, it's powered by a motor.
That's a great way to look at it.
So yes, three-phase power has been around for a long time, and three-phase power was developed precisely to create a rotating field to operate a motor. It takes three wires to provide three-phase power to a motor. We can call them A, B, and C. It's easy.
Often referred to as phases or legs sometimes.
Right. And oftentimes we'll say, okay, this is voltage A, this is voltage B, voltage C, or we'll say phase A, phase B, and phase C, or phase 1, phase 2, and phase 3. There's all sorts of ways of giving them names, but they all amount to three symmetrical balanced three-phase voltages. Three-phase voltage is defined by the line-to-line voltage. In other words, a 480-volt line, you get 480 volts if you measure from A to B or B to C or C to A. That's where the 480 volts is. Now, we also have other voltages. We have 208 that's sort of common on the East Coast. We have 600 volts, which is common in Canada. But almost all installations in the United States are 480 volt three-phase, and 480 volts is defined as the line-to-line voltage.
All those voltages you mentioned are line-to-line because, again, by default, there is no neutral to even measure to. So
right. The only time that neutral is used, it's used for some lighting circuits in factories, but that's it. As far as motors go, they only need the three wires. You don't need a neutral to run the motor.
Well, and if this is developed as a three-wire system, where does that neutral actually come from?
The neutral comes from the way that the secondary of the distribution transformer is connected. Now, in any facility, the voltage that's out on the poles behind the facility is what they call a medium voltage. Okay, now there's three classifications of distribution voltages. What we call low voltage, which is the 480 volts or 600 volts or 208. It's the voltage that you have within the building. Feeding the building, you have a distribution network, which it runs at what they call medium voltage. Typically, this could be anything from 4,000 to 40,000 volts. The number of volts is sort of undefined. And then beyond that, you have what they call the transmission lines, the transmission voltages, and these are usually several 100,000 volts. It could be 300,000, 500,000 volts, and this is what they call high voltage. So high voltage is usually associated with the transmission lines. You come through the transmission lines into a substation. From the substation, you have the distribution lines, which are run at medium voltage. These run out to the facilities where you'll have a transformer outside the building or inside the building, usually outside or up on a pole. This is where the medium voltage is transformed down to the distribution within the building, which is your 480 volts or your 208. So the low voltage refers to the voltage distributed throughout the building.
I definitely had to reframe my thought. When you grow up and 120 volts is in your house, 480 sounds like high voltage to me.
Yes,
But
it is a little bit, when you're in the context of distribution, though, that's what they call low
yes,
voltage.
when you change your frame of reference and realize that there are lines carrying hundreds of thousands of volts, well, now it makes sense that we call 480 a low voltage.
We talk about the three wires. These three wires come from the secondary of this three-phase transform, which converts the medium voltage down to the distribution voltage within the facility. The most common connection is to have three 277-volt windings connected in a Y configuration so that one end of each winding becomes the phase voltage, A, B, or C, and the other ends are all connected together at the center of the Y, and these become the neutral point. Now you say, well, that's 277 volts. That's because 277 is 480 volts divided by the square root of 3. And if you want to find where the square root of 3 comes from, go look at Wikipedia for three-phase systems.
There's a whole derivation on the RMS voltage versus peak and all that, but we are not diving into that.
No, we're
on
not
an audio
diving into that.
podcast.
But it does point out that we get the distinction between what we call line-to-line voltage, which is 480. We would call that a 480-volt system if the line-to-line voltage is 480 volts. The line-to-neutral voltage will be 277 on a 480-volt line-to-line system. Now, we have this neutral here. Typically, the neutral is grounded at the service entrance, almost always connected to ground at the service entrance of the building. It's either connected to ground directly through a wire or through some intentional resistance.
So similar to our house setup once again.
Exactly. The Y-connected configuration with the solidly grounded neutral is the most common three-phase power configuration. If you were to run into probably 99% of the factories, large buildings, any facility that's got 480 volts, three-phase, it is most likely connected as a Y, 277 line to neutral voltage with that neutral solidly grounded at the service entrance of the building.
Now you keep saying solidly grounded. Can you explain what that means?
Yes, that means connected through an actual wire or bus bar connected to the surface of the earth. And that is either done through like a grounding rod, actually hammered into the ground. More than likely, there will be a grounding grid that is associated with the building. In other words, the grounding grid will be laid into the basement floor of the building. The idea is that you have a minimal amount of resistance between the ground of the building and the surface of the earth. Now, that gets into wait a minute now, the surface of the earth has resistance, and that is true. The idea is that you have some potential reference for your facility. It may be here appropriate to talk a little bit about ground, because ground is a term that gets thrown around. We talk about system ground, that is where the power system is grounded, but there's also what we call equipment grounding. And that's for safety's sake. So all the codes will say that every piece of metal that's accessible by a person has to be bonded together with a wire, and that is eventually connected back to the earth ground. That's so that if I walk up and grab the handle of a cabinet and I happen to be leaning against something else, that I don't get a shock.
Or even down to a hand drill that could have a short to the casing. When you pick that tool up off the table, you don't want a shock. That current should be directed to the ground.
Right. And if there's leakage currents and all that, you want those bled off the ground so there's no lethal potential on anything that a person can actually touch.
That makes sense.
So solidly grounded means connecting to ground with no intentional impedance. And a wire is assumed to have zero impedance, even though we all know that wire has resistance and inductance and capacitance, everything else around it. We assume that that piece of wire has zero impedance. And there are advantages to this, and the advantages are, first of all, the voltages are all symmetrical, line to line and line to ground, and they are balanced. If we have identical phase windings, we'll have balanced voltages. Balanced means that they are all 480.0 volts line to line. Now, the other advantage of solid grounding is any capacitively coupled transients from the transformer primary are shunted to ground. And there's a interesting fact of nature, and that is there's capacitance from everything to everything else. So if I have a wire, I have capacitance between that wire and the conduit that's containing it. I have capacitance between the motor windings and the core of the transformer. I have capacitance between adjacent windings. And current can flow through this capacitance. Any two conductors separated by an insulator, it will form a capacitor. And in fact, one of the textbook exercises is if I take two spheres, two concentric spheres, and I can calculate the capacitance, remember all your Maxwell's equations. If you let the outer sphere grow to infinity, that inner sphere will still have what they call capacitance to free space. So there is capacitance between everything and everything else, and having a solidly grounded neutral on the transformer allows that capacitance to somehow or another get back to ground.
So if you had disturbances on the primary side, so your incoming transmission voltage, it will help essentially filter those out of the system.
Well, imagine that lightning strikes a tree near the medium voltage distribution system. So that now all three phases together go up. Lightning could be several 100,000 amps for a couple of microseconds. So this lightning strike will raise all three voltages up. Line to line will be fine, but all three voltages may go 10,000 volts. And that can get capacitively coupled across the transformer to the secondary. So if you don't have a ground connection, you will now have 480 volts, line to line, line to line, and line to line, but you might have 10,000 volts from windings to ground.
And if that makes it to your equipment, it's not going to be happy.
It's not going to be happy. It will break over things. So solidly grounding will allow that capacitively coupled current from the primary to actually go to ground. Now, there are some disadvantages to solidly grounding the neutral. And one of those disadvantages is high phase to ground fault currents. In other words, if I have a short from one of the phase windings to ground, there could be 10,000 to 100,000 amps flowing through that until the breaker can clear, and that will give you what they call an arc flash hazard.
So when we hear that someone's been in a cabinet and they've crossed two phases, and the up-circuit protection is there to kick it off, but it happens so fast you can still have...
Well, it might take a breaker tens of milliseconds to clear. You may have that current available for a reasonable length of time, and that's all depends on what kind of break. Fuses are quicker. That's why we often recommend even semiconductor fuses in front of a drive is to clear this fault current. But that fault current is only limited by the impedance in the circuit, primarily the transformer impedance and the resistance in the wires. So things like branch circuit protection, like fuses and circuit breakers, must be selected to interrupt this high fault current. That's why all equipment comes with what they call an SCCR, or short circuit current rating, meaning that it can withstand this 10,000 amps for whatever time it takes for the circuit protecting device to clear. So if you have a solidly grounded neutral or a solidly grounded system, you do have potential for arcing ground faults. Well, that's one of the things, but you do have this possibility and actual fact of a very high fault current. And the requirement that the interrupting device, whatever you use on there to protect the circuit, has to be able to interrupt this fault current. So how do we fix that? Engineering is the art of deciding what set of problems you're willing to live with. And historically, engineers have made the decision that they would rather live with the problems associated with high fault currents versus the problems associated with having some kind of floating or ungrounded system. Then there are devices, articles of commerce, as it were, that are designed to deal with these fault currents. I can go to a local electrical supplier and I can buy a circuit breaker that's capable of interrupting 100,000 amps. I can buy fuses that can interrupt this 100,000 amps. So the world has learned to deal with the problems associated with a solidly grounded three-phase system. And they would much rather deal with those problems than with the problems associated with, say, not grounding the system.
Understood. So those are the two diametric opposites, but are there other systems out there between solidly grounded and not grounded at all?
Yes, there are. One could add a resistance between the neutral and ground back at the service entrance. And adding this resistance, of course, reduces the line-to-ground fault. Now, it doesn't reduce a line-to-line fault. A line-to-line fault is still a possibility. You still would have to interrupt that. But a line-to-line fault will only produce about 56% of the current that a line-to-ground fault would produce. This has to do with the old square root of 3, and you got the impedances of the winding. So in order to have a line-to-line fault, you have to flow through 2 transformer windings instead of just one. If you have a line-to-ground fault, you go through just one winding, which means just one winding's worth of winding resistance. If you go from line to line, you have to go through 2 windings worth of winding resistance. So the line-to-line fault will be less, typically around 50 to 60% of what a line-to-ground fault would be. So that reduces the requirements on circuit breakers, fuses, and so forth. But the most common fault to have is a line-to-ground fault. Imagine that you're hooking up a motor and you bring the wires into the conduit box. You think you got everything wired up nice, and you close the conduit box, and guess what? One of the wires got pinched between the cover and the box. You tighten the screws up, and there you are. You got a line-to-ground fault. Okay. Or a motor shorts out internally. The winding shorts to the motor case. That's a line-to-ground fault. You very seldom will see a line-to-line fault. They're unusual. They do occur, but it's much more common to have a line-to-ground fault. So using what they call resistance grounding minimizes the current that can flow in a line-to-ground fault. And in fact, most common kind of resistance grounding is what they all call high-resistance ground. And the resistance is usually sized, the ohms of the resistor are sized, so to keep the ground current less than about 10 amps.
So I assume that resistor sits between the neutral then
and the ground. That's correct. And this eliminates most common arc flash hazards. Now, when we talk about an arc flash, we're talking about if we have a short and we vaporize the wire. And there's a lot of explosive energy in vaporizing copper. And again, you can go to YouTube and you'll find all kinds of pictures. If you do a little search on arc flash, you can find little movies of how wire can explode, how an open cabinet can explode. That's why people wear these personal protective equipment whenever they're working on an open powered cabinet. That's why they have the face shields and all that.
Sometimes full-on suits, because you're taking a wire that's intended to maybe have 100 amps run through it, and you could be running 20,000 amps through it, and that causes that vaporizing condition.
Exactly. Power dissipation is proportional to the square of current. So if you double the current, you got 4 times the heat. So if you go up by a factor of 100, you got 10,000 times the amount of heat going into the wire very quickly. It eliminates the arc flash hazard, but it also eliminates arcing ground faults. Now, an arcing ground fault is really nasty because if you have a wire that gets pinched in the conduit box, you get a really strong arc. But you could also have a short circuit that is flowing through an impedance of some kind, usually through an inductance, where the current is relatively small. It might actually be within the normal range of a circuit breaker. So I could have a fault to ground that's only because it's impedance limited to 100 amps on a 200 amp circuit breaker. For instance, let's say I have a winding breakdown within a motor. The insulation breaks down and I got an arc to ground. Well, that arc may not carry much current, but it certainly creates a lot of heat. And an arcing ground fault can cause a fire. The high resistance ground eliminates this possibility because it just limits the current to less than 10 amps. It also, because of the resistance, tends to put some dampening into the inductive circuit. So high resistance ground has a lot of advantages.
It sounds like it has some great advantages, and yet it's not what we most commonly use. Are there disadvantages to it as well?
Yeah. One of the things that you have with high resistance ground is you have to detect a ground fault by some other means. Now, in the solidly grounded system, the circuit breaker detects the ground fault because the ground fault's 10,000 amps, right?
You can't miss
Circuit
it.
breaker, yeah, you can't miss that one. But you could conceivably have a ground fault in a high resistance ground system that would be somewhat difficult to detect because you only got 10 amps, and 10 amps can be easily lost in a 1,000 amp system. So you can have a line to ground fault, and unless you have some special equipment to detect it, it would go undetected. You still measure 480 volts line to line. Now, if you have two line to ground faults on two different phases, well, now you got a line to line fault, that pops the breaker and everything's done. So the way this is typically done is they will measure the current in the grounding resistance. And if you see current flowing in the grounding resistance, that means that you have some kind of a line to ground fault, or you have excessive leakage in one of the lines to ground.
So I understand when you talked about trade-offs of every system, to then have to go and track that down at a large facility.
Well, the people that, again, engineering is the art of deciding what problems you're willing to live with. People that have high resistance ground type installations, and these, by the way, these are growing in popularity because of the arc flash issues and the arcing ground faults and things like that. More and more facilities are installing high resistance grounding. And there are devices that you can buy for detecting where this ground fault has actually occurred and isolating that part of the circuit. But often what happens is they'll put a current meter of some kind, CT, a current transformer, on the neutral grounding resistance and look for current flow in that. And if that current flow becomes excessive, they shut down the system. Open a contactor, shut it down. In some cases, they don't shut it down. They may decide that it's critical to keep operating the facility. We'll go sniff that out by looking for where do we find this leakage.
I was going to say there's a lot of facilities I'm at where they don't want to shut down for any reason they don't have to. So.
Exactly. Now, this brings up an interesting problem. Remember before we said the most common system out there is to have a solidly grounded neutral, or at least have the neutral at the center of a Y. But that's not the only legal possibility. I think it's appropriate here to discuss why would you ground the system. Well, according to IEEE has a standard for grounding, just they have a standard for everything. And they talk about system grounding. The system grounding is the intentional connection of the ground of a phase or a neutral conductor for the purpose of controlling the voltage with respect to earth or ground within predictable limits, and providing for a flow of current that will allow detection of unwanted connection between system conductors and ground. Now, that's right out of this IEEE Standard 142. Such detection may then initiate operation of automatic devices to remove the source of the voltage from these conductors. Now, note they said that the ground does not necessarily have to be the neutral conductor. It could be one of the corners. Now, if I ground a neutral and I measure from ground to any of the phases, I'll see 277 volts. If I ground one of the corners of this supply, now I'll see 0 to that phase, but I'll see 480 volts to the other two phases.
Okay.
So now my phase to ground voltage goes from 277 to 480. Now, it's appropriate here to talk a little bit about common mode, or what they call zero sequence voltages. And this common mode voltage, if you can imagine, it's the algebraic sum of the three-phase voltages to ground at any given time. So this is like VA plus VB plus VC, that voltage with respect to ground, the average of the three voltages. Now, if I want to measure that, one way to do this would be I take three resistors, connect one end to phase A, one end of one resistor to phase B, one end of one resistor to phase C, tie the other three ends of those resistors together so that now I have essentially the common point, the midpoint of the three phases. If I measure from that midpoint to ground, that will be the common mode voltage.
Okay.
Now, if I hook that network up to a solidly grounded Y-connected system, I'll measure 0 between that common connection of the three resistors and ground.
Yes.
If I hook that up to a corner grounded system, I will now measure 277 volts between that center point to ground. So I now have 277 volts AC RMS of common mode voltage. The power guys refer to this as zero sequence voltage. And the way they come about that is a theorem that any three-phase system can be resolved into one forward rotating three-phase system, another reverse rotating three-phase system, and a third alternating system, which they call the zero sequence system. And again, this gets into a fairly technical topic.
I don't believe I've ever actually heard that or dove into that, or I've since erased it from my memory in college.
The whole idea of the reverse rotating field, it's appropriate to running motors because this is why motors have to be derated when running on unbalanced systems. Because an unbalanced system will give you this counter-rotating field to go along with the forward-rotating field. And the counter-rotating field tries to make the motor run backwards, while the forward-rotating component of the field tries to make it run forward. Well, of course, this just results in losses in the motor. That's why motors, if you look at one of these little derating curves, motors have to be derated pretty significantly for even a small amount of line imbalance.
If we go back, there's a standard for grounding a system, but let's answer the question, why do we need two? We've talked about the arc flash and the protection of people. Are there any other reasons? What if we tried to run a whole facility on an ungrounded system?
Well, there are whole facilities that run on ungrounded systems, and they do this because, again, you can have a fault line to ground, and it doesn't shut the building down. And that works okay for things like motors and heating elements and all the loads that you would find in a 1950s style facility. If you were building a facility in 1940 or 1930, 1950, you might elect to not have a grounded three-phase system because you don't want to deal with their whole plant shutting down because you have a line to ground fault. And the codes will grandfather these kind of systems in. If you put in a new installation, you got to ground it. But if some of these existing installations, they let you get by with ungrounded. Now, let's say I put a variable speed drive on this with a typical PWM output. And remember, we discussed a little bit about parasitic capacitances. There's capacitance from everything to everything else. There's capacitance between the leads running from the drive to the motor, and these leads are fed with a PWM, pulse width modulated voltage. In other words, this voltage is switched on and off between the plus and minus bus of the drive. There is a common mode component to this switched voltage, and this component is capacitively coupled between the motor windings and the motor case, also between leads running from the drive to the motor, between those leads and the conduit, which is tied to ground. The way that capacitively coupled current gets back to the DC bus is through the parasitic capacitance between the input wiring of the drive and the power supply, and also through the solid ground that's back at the facility entrance. Okay, that's how it gets back on the wire. That completes the circuit for these capacitively coupled currents. Well, if the input is not grounded, that means that any common mode currents that pass through the parasitic capacitance between the motor winding and the motor case are reflected back onto the input of the drive and end up waving this ungrounded three-phase system around like a flag in the breeze. And that can affect lots of other equipment that was never designed to see these high-frequency currents.
So again, today's facility versus 1950s, where we have computers, we have switching power supplies, we have
PLCs.
Greater sense, industrial networking. Our field buses used to be slow and the signal used to be voltage. Now it's mega or gigabaud and the voltage is millivolts. So this is all way more susceptible to high frequency currents.
Yeah, and the standard cure for this, of course, is to put an isolation transformer in front of the drive that will have a Y-connected secondary that now has a neutral that allows you to ground that neutral local to the variable frequency drives.
That would be my next question. So if we want a VFD in this type of power system, is that the best way to do it? Are there other solutions?
Well, one would think that you could go out and buy an RFI filter to take care of this. because this is what they call EMI, electromagnetic interference. And these filters consist of inductors and capacitors line to line, but also aligned to neutral. They also actually have capacitors to ground. And one of the problems if you don't have a grounded system is, first of all, the voltage now across these capacitors is undefined. And secondly, with all that energy coming back from the capacitive leakage of the output, the PWM part of the drive, usually is enough to pretty much ruin the capacitors that would be in a typical RFI filter. So RFI filters are generally not a good suggestion if you have an ungrounded system. In fact, if you read the fine print on an RFI filter, it will demand that you are connected to a Y-connected, solidly grounded type system. Now, some drive manufacturers will require that their drives are connected to a Y-connected, balanced, three-phase, solidly grounded system.
Do we require that?
No. No, we do not.
Interesting. And do you know why that is?
I suspect there are reasons. We have customers out there who have used competitive drives, and I won't mention the competitors out there, but these competitors often offer soup to nuts type solutions. They can provide you with PLCs, they can provide you with drives, they can provide you with push buttons and everything else, which makes them sort of a one-stop shop, whereas Yaskawa specializes in the manufacture of drives. We make drives. We've had situations where competitive drives have failed in systems with either resistive grounding or in ungrounded systems, and we do not. Our drives go in and work. And the question the customer says, well, why are your drives working? And I said, don't ask me, ask them why theirs fail.
Fair question.
So I would think that if you're going to make an industrial drive and you're going to design this to run on circuits that are designed to power motors, that you would design your drive to run on any circuit that would be out there that would be designed to power a motor. Now that doesn't mean that because a drive can survive operating on some of these ungrounded systems doesn't mean that there are disadvantages, as I said before, with the parasitic capacitances and all that. Because the drive can survive, it doesn't mean that's an optimal situation. The optimal solution for Yaskawa drives is, again, the solidly grounded neutral.
So it could affect longevity of the drive. Could it cause other issues, nuisance trips or faults or things like that?
Yes, you can get some nuisance tripping on a lot of other equipment because the system is ungrounded.
So it may not be the drive actually nuisance tripping, but because of the reflected power that it's distorting onto the system, other devices might trip or give you errant readings if it's a high sensitivity, a level sensor or a flow sensor, things like that.
Now, in most industrial facilities, the wire that goes out to connect to motors and to PLCs and all this wire is carried in a steel conduit, 3 conductors within a steel conduit. There's often a lot of capacitance between these conductors and the conduit. And even in ungrounded systems, that capacitance tends to balance the system out. So even in an ungrounded system, I've heard of people walking out and hanging a voltmeter on there and measuring line-to-ground voltages of 277 volts, even when the system is ungrounded, because of all the parasitic capacitance of the conductors, of the conduits containing them, the wireways and so forth, tend to balance the system. So sometimes that works for you and helps things out in an ungrounded system.
Yeah, I don't know if I can wrap my head around how exactly that works, but it's funny how these things tend to have a way to work themselves out.
Well, when we draw a schematic on paper, we're drawing a highly idealized version of what goes on in the real electrical world. We assume that every wire has zero resistance, zero inductance, and is isolated from everything else, when in fact the wire is really a resistor in series with an inductor with capacitance to everything in its environment. And the same thing with equipment that's connected to this. We assume that the motor, all the current is going through the windings, when in fact there's a significant amount of current that is capacitively coupled between the windings and between the stator windings and the stator laminations, but also between the stator windings and the rotor. I mean, that's why bearings oftentimes will wear out in a motor connected to a variable speed drive, is because that capacitively coupled current flows through the ball bearings and pits the bearings. That's when they talk about reflective wave issues and all this in drives. That all comes back to the imperfection of the circuit.
To me, it's just amazing the way the world works. How, when you think about it, it almost sounds like talking about the Force within Star Wars. Everything is coupled together in some way, in some manifestation.
Well, when you sit here as an application engineer or you're in tech support and you hear the customers call in with all these things, you wonder how anything works, right?
Yeah, absolutely.
But yes, most things do work because all of these effects, even though they're relatively minor. And the world has learned how to deal with them. We've learned how to deal with this. Now, occasionally somebody gets a really clever idea, and then it's like, okay, then these effects all come into play. But for the most part, if you follow the normal wiring practices in a factory, those normal wiring practices, the wires are bundled together, they're in steel conduits, they're bundled together in wireways. The power conductors are generally not run with the phone lines or with the signal conductors. The world has learned to deal with these issues. And it's only once in a while that they pop up in the context of drives, and that's why Yaskawa hires application engineers and tech support people.
Absolutely. If you're ever working in whatever your power system is, you can always call 1-800-Yaskawa and have someone help walk you through. Now, we've talked about specifically why connected systems so far. Is there anything worth touching on a Delta connected system?
Yes, Delta systems do show up. Power companies are really strange in the fact they really try to save money. And it turns out that theoretically, I can get 3 phase voltages with only 2 transformers. Okay, if I hook up the transformers as if I were going to make a delta, and I leave one of them out. And in fact, if you're driving along, you look up and you see a 3-phase installation going into a building, and it's a small building, you'll see 3 pole transformers out there. A pole transformer, just a transformer designed to go on a power pole. Okay, so you look up there, you see 3 transformers. Or if it's a single-phase installation, you'll see 1 transformer. Occasionally, you'll see 2 transformers. And that's because the power companies figured out, you know what, if most of the load in your building is single phase, you have 1 big transformer for your single phase, and you got 1 or 2 3-phase pieces of equipment containing motors, well, they can create that 3rd phase with just 1 extra transformer. And those are often hooked up in what they call an open delta, meaning it's made like you're going to have a delta connection, except you leave 1 of the transformers out. And these are particularly nasty for drives because the impedances are not balanced. You're missing a phase. Okay. Now, the 3-phase voltages are there. If you go out and you measure the 3-phase, you got 480 to 480 and 480. More than likely, you got 480, 480, and 472 or something like that. It'll be oftentimes the phase that's missing the transformer will be a little bit low, but the impedances will be different. And so running from an open delta supply, you often have to derate the drive or add a line reactor. By the way, these open deltas are often prevalent in remote locations. Like if you're going to have an irrigation system that's way out in the middle of nowhere, the power company may elect to only put 2 transformers out there to supply your 3-phase. Now, Yaskawa has a patented feature that we use in an IQ pump and many of our other drives will actually detect this imbalance. Now, the biggest problem with these open delta systems is imbalance. The drive wants to see a balanced 3-phase system. If the 3-phase system is not balanced, we start to put stress on the bus capacitors. The typical ripple on the DC bus of a drive from a balanced 3-phase system occurs at 360 hertz. In other words, 6 times the 60 hertz of the power line.
Okay.
If there's any imbalance, we start to see a 120 hertz component on the DC bus. And the more imbalance we got, the more that 120 hertz gets to be a bigger and bigger part of the ripple.
The amplification of it.
Right. And the worst case is I got single phase and it's all 120 hertz ripple.
Yes.
Right. So Now, in these open delta systems, the imbalance is really bad. So there's a lot of 120 hertz ripple on the bus, and that ripple can be excessive. So Yaskawa came up with a patented system to detect this bus ripple and reduce the speed limit on the drive, the maximum frequency, so the drive actually slows down. And because power is speed multiplied by torque, and power on the input side of the drive is voltage multiplied by current, reducing the power reduces the current on the DC bus, reduces the current coming into the input, and allows the drive to work at some reduced level on these really imbalanced power systems.
And is this a scenario where it would run like that for a long time, or do these systems kind of come in and out of balance depending
They often come in at the typical thing is, guy goes out, puts in an irrigation pump, and he's running on an open delta system, but he doesn't know that. So, or a horribly imbalanced three-phase system. And he can't get his pump up to full speed. Now, he's still pumping water, okay, but not as much as he likes, so he calls and complains. And somebody goes out there and looks at it and says, well, yeah, but look at your voltages are really, you got a highly imbalanced system. And they'll fix it by putting a line reactor in front of the drive. Say, okay, let's stick a 5% line reactor, relatively inexpensive compared to, say, upsizing the drive. And that often fixes the imbalance problems. At least puts things down to where the imbalance is not causing enough bus ripple in the drive to harm the drive. But Yaskawa is the only one that really has this, what we call single-phase foldback feature. It was originally designed for drives running on single phase, but it's turned out to be very helpful on drives running on horribly imbalanced. By horribly imbalanced, I mean more than 2% imbalance of the voltages, line-to-line voltages. And we got it. It's patented.
That wraps up our deep dive into power system configurations and how they impact your VFD applications. Now, we touched on a lot today, but there are still other types of configurations out there. And if you're ever unsure about what you have or how it's going to affect your Yaskawa VFD, never hesitate to give a call into our technical support or our applications team, where you can talk to someone like Joe with years of experience and he'll help you work through it. I'd like to give a big thanks to Joe Pottebaum for walking us through the risks, the gotchas, and a few of the real-world fixes. If you enjoyed today's episode, please like or follow this podcast to stay informed when new episodes launch. And if we're doing a great job, please leave us a 5-star review. Thanks for joining us, and as always, we'll see you next time on VFD Vibes.